Hello everyone, George here, and in this episode we're following up from the last one on vectors, and we're going to use those vectors to do some interesting things. The first thing is we're going to replace things like position and so forth with our vector class. The second thing we're going to do is use it to actually calculate how a ball should properly bounce or reflect off of a screen or one of our walls. So let's go ahead and just assume that we have a wall. Let's make a wall here. Let's make the wall blue. Why not? So we'll just draw a line right there. And this is our wall, and this is the underside of it over here, basically. Now, our wall itself has a direction to it, right? So the direction is this way, but perpendicular to that is what we refer to as the normal direction, which is perpendicular to it. Let's just call that n vector. So we also have, of course, our ball. Now, our ball is coming at this at some vector direction. We don't know what at this time, so we're just going to make one called v, or vector, right there. So there's our v vector. And that's where our ball is coming to. What we need to do is figure out the other vector, that is the reflection vector, which is what comes off of it. And that's going to be something like this. So how do we go from this to our reflected vector, r? Well, there's several different equations you can use, but I like to actually show the way that makes the most sense to me, which is where we break this down into its component pieces and then use them to figure out where it should bounce off the other side. So let's jump to a different color. So if we think about this for a second here, using the dot product, we actually project one vector onto the other. Now in this case, and I made this vector probably a little bit too, let's make this black and erase some of this. In reality, if these are unit vectors, which is what I'm assuming, this is of length 1 and this is of length 1. If we project one vector onto the other, what we're basically doing is taking this vector and determining what it's projected onto in this direction, and then what it's projected onto in this direction, the x, of course, and the y. If you want to think about it with that way, you can. It's not really x and y. It's whatever you want to. But the idea is that this is one axis, this is the other axis, and we're projecting onto it. So a portion of this is projected onto this surface. And you end up with that y term on this way. And then there's another portion of it, of course, projected onto this wall area here, which would, of course, be another vector like that. So let's take a look at this in a little bit more intuitive way really quick. So let's just erase some of this. So what really happens here is when you're dealing with vectors, if you know all this stuff, skip ahead, but you actually compare them at their common point or the origin, unless you're doing some sort of an offset. So really, this is our common point. We're dealing with the initial vector, here. So all of them are at the same location. And what we really want to do is figure out those projections. But you're going to notice that if we project this vector onto the purple one up there, we're actually going to get an inversion of that. We're going to get one in the negative direction. That is, it's going to be pointed this way. If you know anything about the dot product, when you take the dot product, you're going to get a value between +1 and -1. Since we're on this side of it, it's going to end up being a negative value. Let's call this value n projected. Now, we can also calculate from this the amount that's projected onto the wall itself. We can break this down into its two components. How do we do that without knowing what the wall's direction is? Well, we kind of already do. If we subtract this n projection from this vector over here, basically if you subtract it, you take this vector. So let's actually see if we can't do that really quick and not mess this up. So let's do a Control-C and then a Control-V and copy that. What subtraction does is it's like addition, but it reverses the second vector's direction. So what does that do? Well, that vector now is going to be pointed up to here. Okay, that's interesting. So actually, if we were to duplicate that one more time, that is, do that one last time, twice over, we would end up with our reflected vector, which you see right there. And now, those are the steps that are necessary to calculate that final vector we need, which is our reflection vector. Hopefully you were able to follow that. If not, just rewind. That's as clear as I can make it at this point. So now let's jump into Android Studio and begin coding this out. So what I've done is everything's the same, except that I've gone ahead and in my onDraw method, which right now we're using to update elements, which is not a good idea for real games, but okay for right now. But we're going to input all of those different wall bouncing reflection stuff inside of our onDraw. So first thing we need to do is replace these X and Y coordinates with just a single vector. So protected vector 2D position. We're also going to want to replace direction with a vector 2D as well. So the direction is going to tell us where we're moving towards. So before, we were using the direction just to bounce back and forth along the x-axis. Now we need to change our constructor, so we're going to use these x and y values to actually fill in the position and the direction. So let's, of course, make these things something. So let's do new vector 2D, and we will do the same thing for direction right there. Now we're going to take our position and put that there and there. And now our position's information has been populated from these parameters. Next up is direction. Here, the direction is declared as an int. That is no longer true. So let's make that a vector 2D for direction. And now that should work just fine. Now our constructor is updated to work with vectors. Our onDraw, or our draw circle, needs to be fixed. That's going to now use the position.x and the position.y. So we might as well fix that. So what are my plans for this? How are we going to have a direction for our balls? So let's jump over into the custom view, and what we're going to do is actually use, let's see if we can't use this right here. So let's clear this out really fast. So let's just do Shift 5 and background, thank you. What we're going to do with this is I'm going to use the user's first press. Whoops, Control D, brush. So their first press is going to get stored, and that's where they decided to press down on the screen. That's the on down. And then they're going to move their finger all over the place. We're going to continually save that. And then finally, they're going to remove their finger from the screen. So say here. This now maps out a vector going from the initial point, 0, to 1. And there becomes our vector. And that's now going to be used as our direction for where the user wants to fire the ball off to. And we'll also use the magnitude of this thing to determine how fast it's going to move. Given that information, we need to update onTouch. Right now, we only handle action up. We're going to need to handle two other cases. Case motion event dot action underscore down when the user first presses it. And then our next case is when the motion event finds out that we've moved around. So let's do move, colon, and break. We're going to need to store this information. And the best way to do that is, of course, to create some variables for us to work with inside of our class. So let's create 3 vectors. The first one is where we touched, and of course, the next one is going to be the last position the person moved it to until they brought their finger up. And then we're going to, of course, also store the direction that they decided to touch. So let's do protected vector 2D initial touch, and just set that to a new vector 2D. Now let's do a protected vector 2D delta touch is what I'll call it. So the idea is that's our change as we've moved our finger around. And then finally protected vector 2D direction touch. Now that we've created these vectors, we can work with them down here. So when we first press down on the screen, initial touch.x is going to be equal to motion event.getX. Then our initial touch touch.y is equal to motion event.getY. Now I'm also going to initialize the delta touch at this point as well. The reason for that is because at the start of the game, the user might somehow not move their finger in any direction, and we just pop it down immediately, in which case we're going to get a 0 direction and the sphere is just going to stay there on the screen. I would rather give it some sort of direction moving. So by default, we're going to do delta touch, enter, copy that down there, and we're just going to, let's just say it always moves off to the right. We're going to normalize these vectors anyway, so it doesn't matter. 10's a little bit large, let's just go with 1. And that's it for when the user presses on the screen. Next up is remembering or continually storing as they move their finger across the screen that delta touch value. And this we're going to, of course, just get our motion event in the X and the Y and store that. Now, the interesting stuff happens when we decide to pick our finger up off the screen. That's when we're going to fire that ball off in a particular direction. So we're going to now need to calculate our direction, and that's going to be the subtraction of our delta touch vector from our initial touch vector. So let's do direction touch is going to be equal to vector 2D dot subtract. And with that, well, actually, that's going to create a new vector. And it's going to then be delta touch and initial touch. And that's it for that. Now we're going to pass this value in. The 1 is now the direction, but this direction actually should be normalized beforehand. So what we really should do is dot normalize the returned value and then pass it in over there. Our RGB is good. We also need to work with the magnitude of this thing, and we shouldn't normalize it on the same line in that case. So let's make a small change. Let's do float magnitude is going to be equal to direction touch dot magnitude. And then after that's calculated, we can go ahead and normalize our direction touch. We're going to pass the magnitude in as a speed parameter. That is, let's see, in our parameter list, Control P. So in our parameter list, that is the 1, 2, 3, that's the 4th variable or parameter. So 1, 2, 3, 4, that's the 50 right here. So let's replace that. We're probably going to want to make it so the magnitude isn't too colossally large. So we might want to do a test on that. So if magnitude is greater than, I don't know, 50 pixels, then magnitude is just going to be equal to 50. That's our maximum. We've pretty much handled the script. That is dealing with picking up our finger and putting it down and firing off a new ball. But there is one thing I do want to do very quickly. I want to add to this the ability to draw the direction so the user understands where they started from and where they're actually pointing to now. So let's create a new function called protected void draw direction. This is going to take in the canvas object and just draw a line for us. So let's do canvas dot draw line. This is going to take the initial position in the X direction, the initial position in the Y direction, and then the delta, not delta time, delta touch dot X and delta touch dot Y. To draw our line, it also needs a paint object. So let's create a new paint object up here. Let's call this paint line color is equal to a new paint object. And then we'll set this thing up in just a second. Whoops, that's what I want. And let's make that protected as well. So line color, you come along in here and we'll set you up. So line color dot set color, let's do color dot red, and the line color width set, let's see, stroke width, let's just make that, I don't know, 10 pixels wide, give the user a lot to see, and maybe 10's a bit much. Let's do 5. 5 sounds good. So now let's use the line color down here and pass that to this function. Now we don't always want to draw the line. We only want to draw it when the user is pressed down. So we need to store a Boolean that tells us whether or not things have been pressed. So let's do a new protected Boolean is touch detected. Something like that is equal to false at first. Come on down here. So when we touch, this is true. And when we take our finger off, this is false. And now we just need to do a check inside of where we're going to call it, which is going to be right up here. So if is touch detected, then we can do our draw direction and pass in our canvas object. And that's it for drawing and handling all that stuff. Now we just need to get to the meat of things and handle that bouncing ball and actually doing all of our calculations. In our constructor, we get a direction. There's nothing saying that direction's actually normalized, so we should probably do a dot normalize on this object before we store it away. Now with an onDraw, we're going to handle 4 conditions. Just like before, we're going to have a bunch of if statements and then else if statements, which are going to revolve around whether or not we've hit the boundaries on the sides of our area. So we're going to want to check for if the position dot x is less than the radius. That is whether or not we've touched that side. And if it is, we are going to set the position to be equal to 0, position.x equal to 0 plus the radius. And then we're going to need to calculate our bounce. And then the next thing we're going to do is, just like last time, we're going to do our sound manager.getInstance.play sound manager.sound boop. So that should look exactly the same as last time. But now we're going to copy this a few times. Let's do v, and these are going to be else ifs. And they're going to handle the other sides of our window. So this one was position.x is less than the radius. We want to see now if we're going to be greater than the width of this thing. So that's the custom view dot get screen width plus our radius. Subtract our radius. We want to stay on the screen. In which case, we're going to keep ourselves on the screen by setting our location to be equal to the position.x with the screen width minus our radius. We're once again going to have to calculate our bounce, and we're going to play that lovely boop sound. Now we're going to deal with the y directions. So if we are, so this was the, let's see, this is the left side of the screen. This is the right side of the screen. This is going to be the top of the screen or the bottom, if you think about it, because the y-axis has a 0 at the top of the screen and it goes larger as we go down, and this is going to be the bottom of the screen. Okay, so here, if the position.y is less than the radius, we're going to set the y equal to 0 plus the radius. We're going to do our sound. Here we're going to do position.y if that's greater than our custom view dot get height minus the radius, and that'll keep us contained. And once again, we're going to grab this and set that equal to where we should be. And that should be a y. Okay, so now we're ready to do the real calculation stuff. But first, we need to update our position. This is very similar to last time. We're going to be calculating a delta position, but now we're doing it with our vectors. So let's do a vector 2D. Delta position is going to be equal to a vector 2D dot scalar. And this is going to take in a few values. First is the direction that we're moving in. Next up is our speed times custom view dot delta time. So think about it. This is our direction, where we're moving towards, and we're creating a vector that takes into consideration a unit vector for direction and multiplies that by speed times delta time. That makes a very small vector because delta time is very small. This is telling us how much we've moved in that amount of time along that particular vector. Then we're going to add that to our current position. So let's do position.add and then delta position. And that's it for updating our location on the screen. Now we just need to handle bouncing around. We're going to create a separate method for this called protected vector 2D calculate reflection. It's going to take in a vector 2D, and that's going to be our whatever our direction is, basically. Let's just call it direction. Why not? And then it's also going to take in another vector 2D, and that's going to be the normal vector of the wall. Right now, all of our walls, we know their orientation, so we can easily figure out what their perpendicular vector is. Just like as I explained before, we're going to fall through all those steps. First, we're going to calculate our projected vector onto the normal one. Then we're going to calculate our vector onto the wall. And then from those two vectors, we'll be able to calculate the reflected one. So first, let's do our dot product. So that's float is going to be equal to the projected vector on the normal wall. So that's going to be our projection scalar value, since we're just doing the dot product. So that's going to be vector 2D dot dot. And we're going to pass in the normal vector and our direction vector. So now we know how much the direction vector coincides with the normal vector, and they should both be unit vectors. Then we're going to do a vector 2D projection vector is going to be equal to our vector 2D dot scalar. So we're going to multiply our normal vector by the projection scalar that we just created. That's going to shrink that unit vector to the proper size. How much of the direction vector coincides with our normal vector? Then we're going to calculate that 90-degree offset from the projection vector, which I'm going to call projection wall. And that's going to be a vector 2D, and that's our subtraction step. So subtract, and we're going to subtract the direction from the normal or projection vector. Excuse me, there we are. And finally now, we get to create our reflected vector. Vector 2D reflected is going to be equal to vector 2D dot subtract, and we're going to subtract from project wall the normal. And finally, we're going to, this one, project vector, excuse me. And now we're going to return reflected. And now all we have to do is make sure we do the right one for each of these. So under calculate reflection here, we want to set this equal to our new direction. Calculate reflection is going to take in our direction, which is just direct. I mean, really, we don't need to pass a direction since it's inside of this class. We could do all this stuff inside of it, but I'm going to just do it this way anyway. And now we need to know the vector direction. It might be really good idea for us to extend our vector 2D class just a tiny bit and add to it some static vectors, some unit vectors that are in common directions that we're probably going to need a lot of. So let's create a public static final vector 2D, and let's call this, whoops, not a method. Let's call this up is equal to a new vector 2D, and up is going to be 0.0f, 1.0f. So let's do this a few more times for each of the other ones. So we have up, down, left, oops, left, and right. And of course, just flipping everything here. So, whoops, that's not right. That's correct. Now these ones get flipped over, and these become 0. And left is going to be pointing to the left, which is our negative direction, and right will be in the positive direction. But now we have some convenient vectors that we can use all over the place, especially over here. Since our walls are up, down, left, and right, we can work with them here. So if we're on the left side of the screen, this side, so if this is our screen right here, we're actually going to want to, the normal is to the right. If we're on the left side, it's to the right. If we're on the right side, it's to the left. It's a little bit different though, because we haven't done any kind of coordinate changing yet, but if you remember, this is positive and this is positive. So therefore, if we're at the top of the screen as we're considering it, we actually want to go in the up direction. And if we're at the bottom of the screen, but because that's more positive, we actually want to go in the down direction. So hopefully that made sense. For our left, we're going to go right. So that's going to be vector 2D right. And for the right one, we're going to go in the opposite direction. So let's copy this line and paste it. So there we are. And this is going to be left. And now we're going to do the final ones. So if we're at the top of our screen, we're actually going to want to go in the top direction, or up, excuse me. And if we're at the bottom, we're also going to want to go down. All right. Going back over to our custom view, it looks like everything's going to get drawn. Things are going to be added just fine. Let's give this a go. Let's hit run. Pick my device. So here's our screen. Let's see if we get any problems. So we can see our line is being drawn perfectly. Let's release a ball. Now our ball is moving. Hits and bounces. So let's see if we make a very slow line or a big line. They move at different rates. It's very hard to tell. I might want to increase available rates. Let's see if we can do a really, oh yeah, they're definitely moving at different rates. And we can see they're bouncing correctly off the walls as we would anticipate. We'll make one going almost perfectly straight. Boom, and it bounces right off. All right, great. So let's stop all those boops. So that's great. So we have successfully implemented a Vector 2D class, brought it into our Canvas system, and we've now used it to control bouncing balls that go all over the screen and properly reflect off of them. So there's a lot more you can do with this, and we're going to have a few more Android videos after this showing you other ways you can use our vector class to do really interesting effects, so long as you put them with time. I hope you enjoyed this video. Remember, if you did, please put a like down below, or if you're really interested in the continuation of the series, consider subscribing to watch more. I will see you all later. So long, goodbye.